All right, welcome to the post-exam 3 review material for this is Math 234 in the summer of 2023. And again, we're reviewing the content that happens after exam 3, but is also going to be featured on the final exam. Speaking of the content that's on the final exam, the course is split up roughly into 4 sections: is an exam 1 content, exam 2 content, exam 3 content, and now post exam 3 content. And the final exam will feature about a quarter of each of those four sections. So the rough weight of the final exam is about evenly split between the 4 sections of content, with maybe a slight emphasis on this post-exam 3 content. We haven't taken an exam on it yet, but no more than about like 30% of the total exam. So final exam is cumulative. Today we'll just be focusing on the stuff that we have not featured in an exam review yet. So the post-exam 3 material. And also the post-course survey is currently available on D2L. It's worth a half percentage point toward your final grade. So you should take it. And in fact, if you haven't taken it right now, you should pause this video, take it right now, and then come back. We will still be here. So again, if you haven't taken it, pause the video, take it now. All right, and welcome back. Let's get this review started. So this post-exam 3 material focuses on the second half of chapter 16. The main 3 sections, the ones that you can definitely expect to be a large question on the final exam, will be from Green's theorem, Stokes' theorem, and the divergence theorem. Definitely expect one question from each of those sections, and you'll probably get a good idea of what to expect from those sections based on the problems that we'll see up ahead in this review. But before we get into Green's theorem, I want to first talk about curl and divergence, make sure we're good to go on those 2 concepts, because then those will play a big part in understanding Green's theorem and Stokes' theorem, and also the divergence theorem, since we'll need the divergence for the divergence theorem. Right, let's do this. So step 1, here's some vector field. It's got 3 components. We usually call them P, Q, and R in alphabetical order for the X, Y, and Z components. So P is this guy, Q, this guy, it's the Y component, R then is this guy, the Z component. I mean, we just give him those labels because we want to be able to call them something. And so then the curl is going to be the cross product of the partial derivative operator and our field. And it's got a simplified form that we see in front of us: R partial Y minus Q partial Z, and blah, 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 so on down. So that each component of the curl does not contain any piece for the component position that it's in. What I mean by that is that the X component of the curl does not have any of the X components of F. So it does not have P, which is the X component of F, nor does it have any partial X in there. So it's because it's in the X position, it does but all of the other variables, both of the other variables. So if I wanted to go through and calculate this curl, I'm going to need R partial Y, so the Z component with a partial with respect to Y, that looks like 3x. It's going to be R partial Y minus Q partial Z. I need the yellow one. It's Z partial. I believe that's negative X. Right, then up next, P partial Z. Coming in, that's going to be Y. Right, 2x plus yz, I need partial z, so just the y survives. Minus, hey, come back. Minus r partial x. We do partial x on that thing, I believe we'll be left with 3y. And then finally, I need q partial x. The other thing partial x, it looks like negative z minus p partial y. Yeah, p partial y. If we do a y derivative on that thing, we're just going to be left with z. So negative z minus z. Meaning our result, I've got 4x, negative 2y, and negative 2y, and negative 2z. I believe that's what I get when I put it all together. Yeah, cool. So that's our curl. That's definitely the harder of the two to calculate. The divergence of f is just the dot product of that partial derivative operator and our field, which is just the take each partial derivative once and write down the line. So I need p partial x plus q partial y plus r partial z. So all of the partial derivatives that did not show up in the curl do show up in the divergence. And also remember that the curl is a vector operator. So we get a vector result. Well, they're all vector operators. The curl gives a vector result. So the solution to a curl is a vector. Oftentimes we'll end up taking the magnitude of that vector or maybe just one specific component of that vector. But the curl itself should produce a vector instead of a scalar. Whereas the divergence, being a dot product, that result is a scalar. So our answer is just a number by the time we're done with the divergence. So going down the line, p partial x is 2 plus q partial y is negative 2 plus r partial z is positive 2 again. So 2 minus 2 plus 2, I believe that's 2. Cool. So there's some basic stuff for curl and divergence, just calculating one of each for a vector field. An application of that will take us back to some of the stuff that we were doing earlier in chapter 16. In particular, where we looked at some conservative vector fields. We had a calculation to come up with that, which is basically, we want to assume that our field is the gradient of some scalar function. So I want to check all of the mixed partial derivative terms to see if they come out to be the same thing. If they do, we've got a conservative vector field. More on that in a minute. Because once we got to the curl and divergence, we introduced a sort of a shortcut way for establishing if a vector field is conservative. Instead of needing a specific formula that we're going to remember, we can just say, all right, look at the curl. If the curl of our vector field comes out to 0, we have a conservative vector field. And if that curl is non-zero, then it is not conservative. So those are the two options I wrote over there on the left for conservative versus not conservative. If our curl is 0, we're good. If our curl is not 0, then we're not conservative. So if we take a look at that curl of f, similar calculation to the one that we saw above, I need r partial y. Again, this guy, we'll just relabel things again. That guy is going to be r. This guy is going to be q. This guy is going to be p. P, q, and r. And we'll take our curl. So I want r partial y, which should give me 6xy z squared. Minus q partial z, So if we take our derivative there, partial of z, 3 times 2 is 6xyz squared. Oh, and if we take that difference, we'll see we get 0. So again, what the maybe what we want to be thinking about here is that we want to assume that R is already a partial Z and Q is already a partial Y. So I want to compare those two terms together with adding in the missing mixed derivative piece. So if R already has its partial Z, I want to do partial Y on it when I compare it to Q. I'm assuming Q already had a partial Y. So now I'm going to do partial Z when I compare it to R. That's the idea behind this curl working out for us. And of course, instead of saying those two pieces are equal, we'll just say that their difference is 0, which is, 6 of one, half a dozen of the other, is, I believe, the expression. I digress again. Okay, on to the next term, P partial Y. Or nope, that's wrong. P partial Z is the next one we want. Yeah, because we're going for the middle term, so we don't have anything to do with Y. P partial Z looks like it's going to be 3y squared z squared. Three y squared z squared. Next to that, I want to subtract r partial x, which is 3y squared z squared. And we see that that will also add up to 0. Finally, I'm going to want q partial x, which looks like 2y z cubed plus 1. And subtract from that p partial y. So if I do a y derivative over there, looks like I'll get 2y z cubed plus 0 plus 1. Which once again, that should add up to 0. So we see in simplifying each of those 3 steps, 0, 0, 0, or rather simplifying each of those 3 components, I got that my curl came out to the 0 vector. Every entry is 0. Meaning the thing we have here is indeed a conservative vector field. We'll pick option A. Because it's conservative, that means we should be able to find some original function f whose gradient would come back out to our vector field. So to find that function, what we'll want to do is integrate each of our 3 pieces, each of our 3 components with respect to their own position. So we're going to integrate the x component with respect to x. We're going to integrate the y component with respect to y, z component with respect to z, and then use that to reconstruct our original function. So if I do the x piece, do that one first. I've got an x, y squared, z cubed, plus x, plus xy. And in addition to that, I'm going to gray this part out. In addition to that, there could be some other function. I'm going to run out of letters here in a minute. Let's do h of y and z. So there could be some extra function here that depends only on y and z that gets lost when we do the x partial derivative. If there are any terms that do not depend on x, their derivative will be 0, meaning integrating with respect to x will not recover those terms, which is why we then also need to do the other derivatives. So we do a y derivative, and we'll get 2xy squared z cubed over 2, which I'll simplify to x y squared z cubed plus xy. Clean that a little bit so that it looks nice. And then in addition to those terms, there could be some other function that depends only on x and z, where all of the terms in that extra function would get lost when we did a y partial. Because any term that does not depend on y, its derivative will be 0 when we do a partial with respect to y, meaning that if there are terms there, we'll need the x integral and the z integral to recover those terms. So the same thing, we do our z partial integration, we'll get xy squared z cubed again. That's the only term in R, so we only get one that shows up here. And again, plus some other function. I used a g, I used an h. How about j? J gets left off a lot. Call this other function j. This time, a function that might depend only on x and y. Because again, if we took a z partial, we'd lose information about those terms. So these are our 3 incomplete guesses at what f is going to look like. And we'll use those 3 to reconstruct what the original function f should have looked like. Which means I'm going to look through those functions and every unique term gets put into f. So our function f should be, well, we'll start with xy squared z cubed, because that term appears in all 3 of our integration terms. All right, so for each of those, they all show up in f. But I don't want to include that function 3 different times. I only want to include it the once. Because that one term, then when I take partial derivatives, will show up in each of the other 3 partials. So then that takes care of that term, which shows up in all 3. Up next, I've got this plus x term that only shows up in the x integral because that term depends only on x. So we know that that term would not show up in either of the y or z partials, which means that plus x is one of the pieces that would hang out in that g function and also in that j function. We know that term could exist, but doing a y integral or a z integral isn't going to recover that term for us. So we got to bring this guy down from our x partial. Right. Then up next, I see a plus xy that shows up in our x and our y integral terms. It makes sense that it wouldn't show up anywhere else, or specifically wouldn't show up in the z term, because that term has got no dependency on z. Or rather, it won't show up in the z partial, because that term has no dependency on z. So at that point, we've established each of our 3, we've gone through all 3 of our integral suggestion functions, picked out each unique term and put it into f. So this must have been our original function with a final, if this was back in like a Calc 1 class, we'd call it plus c, though it seems like in multivariable functions, we've switched over to calling it plus k instead. But this time, k or c, whichever letter you want to throw in there, is just a constant number. Just like, when you do a regular Calc 1 integral, If you leave it as an indefinite integral, you have to add a plus c because there could be any arbitrary constant that shows up, because we lose all information about constants when we take a derivative. Same thing here. We'll just throw in an extra plus a constant, because if there were one, we'd have no way of figuring out what it was without without some sort of initial condition, some initial value. Cool. And we can see in web work, it already added that plus k for us. That's that part just off to the right there. Cool. So that's conservative vector fields. And in particular, reconstructing a function originally. So past that, oh boy. Past that, I do want to talk about one more example involving this stuff. But it looks like I may have lost it. So give me just a second. To bring it back in. Oh, here it is. So going over just a more complete or full explanation of a completed vector field or a conservative vector field. So I'm just going to claim at the beginning, the vector field in front of us is conservative. I've already done the work out of this one, so just want to highlight the overview of what's going on. So here's our conservative vector field. Oh boy. I pulled this example out of the 16.3 notes, so back when we did the fundamental theorem of line integrals. But I think this example also got copy and pasted into the curl and divergence section. But cool. So here's a conservative vector field. I just want to explain why we know it's conservative and how we get to that original function. So we want f to be the gradient of some scalar function f. Meaning when we say f is PQR, what we're really trying to say is that big capital F, the vector field, is the x partial of f, then the y partial of f, then the z partial of f. Right? They're all in the little f. I'm looking at this guy right here. So we're just assigning P, Q, and R arbitrarily to be the labels on the three components of big F, the vector field. But what I'm thinking in my head is that I want each of those components to be a partial derivative, because that's what it's going to mean for a vector field to be conservative, is that I got the field by taking the gradient of some scalar function. Cool. So the thing, actually, I'm going to leave that highlighted because that's important. So the things then that we want to show in order to prove that something is conservative is that all of the mixed partial terms are equal regardless of the order that I take them in. So I want the xy partial to be equal to the yx partial, shouldn't matter what order I take them in. Then I want the xz partial and the zx partial to be equal. I want the yz partial and the zy partial to be equal. So that's what I want to show from a conservative vector field, that those partials are the same. And again, I'm assuming one partial has already been taken, so I just need to do the other one to complete the process. And these are actually shown in backwards order from the way that they'll show up in the curl. So the term that would be in the curl is actually the one I've got on the bottom of the table. The first term in the curl is at the bottom of the table. Last term in the curl is at the top of the table, because I just organized it slightly differently for this example. But we'll see that the same idea is going to apply here. So again, I'll assume P has already had its x partial, so I want to do its y and its z partial. I'll assume Q already had its y partial done, so I want to do x and z partial. Same thing for R over there. And so then I just need to look across the columns, look across the rows to verify that each of these mixed partial derivative terms are equal to each other, which we can see that in this case they are. All right, so like across the bottom row, 6xyz squared in the middle row or in the middle column is equal to 6xyz squared over on the right column. Right, I'm looking at like these guys right here. see that those are equal. The part on the right is just the, writing out the step that I'm verifying, hey, yeah, those are equal to each other. The way that shows up in the curl is by taking the difference between the two things and seeing that we get 0. So if two things are equal, we take the difference, the result should be 0. So that's our verification to show that the vector field is conservative, meaning we ought to be able to find that function f. So to find that original function, I integrate each of my 3 components with respect to the position that they're in, simplify to some expression or some formula, some guess at what f is. And again, I reconstruct f by taking every unique term that shows up in each of those 3 integrations. So you can see drawn a bunch of arrows to see where stuff goes from, and hopefully that's not too wild. I was, hoping it would look relatively clean when I drew these arrows in. I'm kind of happy with how it turned out. But we can see from here, or in this final function f I've got down at the bottom, I'm pulling every unique term from the 3 integrations above. And again, I've got this x, y squared, z cubed. It shows up in every term. So I only include it in f once, because when I do the verification step that I'll take in a second, we'll see that that one term is enough to show up 3 different times in the gradient. Yeah, cool. So just wrote in an extra note here. F is not the sum of the 3 components, but is instead the union of all the unique terms. And then go through the step of taking the gradient of that function. So I've got f up here. I want the gradient of it, which means x partial, y partial, z partial. And I'll see if I take the gradient of that thing, I get back to the original field f, which is the step I'm showing out here. So those are conservative vector fields and how we reconstruct an initial function. Cool. So why are we doing all that? Well, all of this is to get an understanding of these new theorems that we're introducing in this post-exam 3 content, specifically Green's theorem, Stokes' theorem, and the divergence theorem. Because while they are 3 different theorems, and they are probably the hardest theorems we've seen in the course, they all have a common root or a common ancestor, if you will, something like that. They're all coming from the same idea. So Green's theorem, Stokes' theorem, and the divergence theorem are all the fundamental theorem of calculus, but evolved into multivariable. So fundamental theorem of calculus is the one that's just peeking up at the bottom of the screen right now. That's the one that said that if I integrated some function, so I've got some capital F prime, so I'm going to integrate capital F prime, its integral will be capital F, right? So we can integrate up to that function. But the fundamental theorem was the one that said that if I do the definite integral of that function, then it's the same as evaluating the integrated function at the boundary points at a and b. So f of b minus f of a. That was our thing that we did back in the fundamental theorem of calculus from all the way back in Calc 1. So the reason that we care about finding this scalar function up above, where the gradient of that function is our vector field, that's so that we can adapt the fundamental theorem of calculus to line integrals. And then that's where we call it just the fundamental theorem for line integrals instead of fundamental theorem of calculus, but it's the same idea. I need to have some integratable function, or some f that's differentiable, so that if I integrate its gradient, I can say that that's the same thing as evaluating the original function, which is little f. That's what I'm calling the original function, or maybe the progenitor function, something like that. So that function little f, if I evaluate it at the points a and b, that's the same as the line integral of that gradient field f along any curve I choose to take between those 2 points. Because that's what we need to have a conservative vector field, is that as long as our vector field is conservative, the specific path we take to get from point A to point B will not matter for this integration step. I can just look at an evaluation at the end point minus an evaluation at the beginning point. So that was our fundamental theorem of calculus, which was, again, I want to say that a definite integral of a nice enough function is just equal to an evaluation of the function at its boundary points. And here I'm calling them boundary points instead of endpoints, because I want to emphasize that we're evaluating the function along the boundary, because that's the idea that we want to evolve into higher dimensions. So then when we go to look at Green's theorem, which will again be an extension or an evolution of the fundamental theorem of calculus, I want to equate a double integral of some function to a single line integral of a very related function that's evaluated only on the boundary of the region that I was integrating over. So a double integral, I have to evaluate it over some 2D region labeled here as D, but I can say that if I have the right kind of function, or nice enough function, that's equal to the line integral only along the boundary. So I'm evaluating one step of the function along the boundary instead of through the entire region in the middle. And when I say that there's a nice enough function, I mean that there's some sort of derivative element that's going on. Rather than diving too much into Green's theorem, I'm going to move ahead to talk about Stokes' theorem and then relate it back, because I think it'll be easier to understand that way. That nice enough function is really going to end up being the curl of f when we're looking at either Stokes' theorem or Green's theorem. There's actually even a divergence theorem element too, or a divergence, but I'm getting ahead of myself. Stokes' theorem, we're going to say that the double integral of the curl over some surface S is equal to just a line integral along the boundary of that surface. So I'm reducing in each of these steps, every fundamental theorem of calculus step is reducing the overall integral count by 1 when we move over to the right side. Works out real nice if we're only taking a single integral, but when we're doing multiple integrals in these higher level calculations, there's still one or two integrals that have to be left over. But super cool. Stokes' theorem, the curl of f, which is some form of f's derivative, because we look at a few different kinds of derivatives. And we'll look at the integral of the curl is equal to a line integral of just the original function, so not the curl part. Because again, the curl is the derivative part. We spend a derivative to do an integral, and hey, look, we reduced our integral count by 1. Hopefully some of that is making sense. I know it certainly didn't back when I took Calc 3. A lot of this stuff will come with time. But so I promised I was going to relate Stokes' theorem back to Green's theorem, because they are very similar theorems. The major difference between them is just the number of dimensions that we're applying them to. In both Stokes and Green's theorem, we are evaluating a double integral along some thin 2D surface. So if we parameterize whatever thing it is that we're doing, we'll only need 2 parameters to do it. Again, it's like a 2-dimensional shape. It's thin, meaning it doesn't have depth. In both cases, we're looking at 2D surfaces. But Stokes' theorem is an application in 3 space. So I might have a thin 2D surface, but it's curved through 3 space. So Stokes' theorem applies there. Whereas Green's theorem is specifically applying only to 2 space. So I have a 2D object in 2 space with Green's theorem, whereas Stokes' theorem is a 2D object in 3 space. That's the major difference between the 2 functions, because otherwise it's Green's theorem honestly just a specific case of Stokes' theorem, if you look at it from that perspective. But they're important enough theorems that each one got named after, a guy that did a thing way back in the day of mathematics, probably Stokes and Green. But again, I digress. You might have also seen in the Green's theorem part 2 stuff that we did, where we were looking at two-dimensional flux. We also had a version that looked at the divergence, the double integral of the divergence of f was equal to some line integral along the boundary. So there are two sort of separate versions of Green's theorem, which is why it's split up into a part 1 and a part 2. The part 1 version of Green's theorem looks specifically at the line integral of our field f dotted with its parallel vectors or its derivative vectors being the parallel vector. Then in part 2, we switch to looking at the field dotted with the normal vector as opposed to the parallel vector. So when we look at the dot with the normal vector, that's when we're looking at two-dimensional flux that just goes through a line or a curve instead of through a surface. And when we're doing that normal vector line integral, then we'll say it's equal to the double integral of the divergence instead of the curl. So if we switch to the field dot with the normal vector, that'll relate to the divergence. And if we do the field dotted with its derivative or parallel vector, then we'll set it equal to the double integral of the curl instead. So that's not something specifically that you'll need to remember for the final exam, although it is the step that finally made Green's theorem and Stokes' theorem click for me when I went back to learn it like a year or two after I took Calc 3, because it's, again, this stuff's pretty hard. So if you're feeling overwhelmed by these new theorems, you're in good company. Finally, the divergence theorem, we're gonna step up the fundamental theorem to solids, so 3D solids instead of surfaces. And so the divergence theorem says that the triple integral of the divergence of f over a solid region, so a three-dimensional solid region, is equal to the double integral along that solid's boundary. So the surface that surrounds the boundary. So for, to give an example here, if we're just talking about a sphere, the triple integral of the divergence would be through the entire sphere, so the whole thing, all of its insides up to its edge, whereas the double integral of our field f will happen only along the surface of that sphere, which is why we also had to do a section on surface integrals, because it turns out they end up being pretty important, really for both Stokes' theorem and for the divergence theorem, because they're both looking at evaluating integrals along surfaces. Cool. So this diagram right here is really what multivariable calculus is trying to build toward the entire time, is being able to get to a point where we have an understanding of the fundamental theorem of calculus in higher dimensions. So this diagram right here, if we could sum up Calc 3 in one way oversimplified image, this is probably the one I would pick. Practically, it doesn't actually help you learn how to do any of the calculations, which is why we're going to go over some more examples. All right. Definitely went off on a long enough tangent there. So let's get back in with an easy one. So I want to calculate the curl of f dot, or blah, that's not at all what I wanted. Let me back up. I want to calculate the line integral of f dot dr along the curve C, where f is the field provided, and C is the positively oriented boundary curve of a region D that has an area of 6. So it doesn't really tell us hardly anything about this curve or that region, but it does tell us precisely enough to evaluate this thing the easy way. So the statement of Green's theorem says that as long as I've got this thing here, that line integral along the curve C, as long as it is the closed boundary curve of a region D, I can switch it over to a double integral instead. So the line integral of f dot dr. So it's being dotted with its parallel vector here, meaning we're using the phase one or part one of Green's theorem. It is equal to the double integral over the 2D region D of q partial x minus t partial y dA. So that's our Green's theorem statement. One extra thing that I want to add here to the notation is one that we don't see as much in the math world of things, but it does show up significantly more often if you're in like a physics or an engineering field or class or whatever. And that's this little circle that I just put around my line integral on the left. So putting that circle through the integration symbol really is just there to indicate that the line integral I'm doing is on a closed curve C. The reason why it doesn't tend to show up in math a whole lot is that notation is just there to signal a concept of sorts. Adding that circle doesn't actually change the calculus or the calculations that we're doing. So a little circle, no impact on the calculus. It's just there to indicate a concept, saying specifically here that my curve C is closed. Doesn't impact the actual math that you do, which again is why I think that our textbook tends to leave it out. But I know there are some cases where you will see that notation, and so hopefully the primer you get here means that when you hear about it again, you'll be in a better position to understand what it means. That's the dream anyway. So what are we doing here? I should label my stuff because I called things P and Q, but it's always worth labeling, hey, this thing is P and that thing is Q every time. You certainly don't need to do that when you're doing your own work, but since I want mine to be legible and learnable, I'll keep labeling things. So that's my P and my Q. I'm going to need partial derivatives with the opposite variable to its position. So I'm going to start with Q, which is the y coordinate. Because it's the y coordinate, I want its x derivative. And that x derivative is -7. Or that x partial, I guess I should say. Cool. Then come over to P, which is the x coordinate. I want its y partial. And that y partial is 2. dA over region D. Still don't really have anything for my bounds yet, but as we'll see in a second, we're going to get real crafty so that we don't even need them. So this is the double integral, or -9 times the double integral of dA over my region D. And here's that super nice trick. All I have to integrate here, or all I have to double integrate here, is my integration token dA. That's all that's on the end. That's all that I have for my integrand is dA. And as I said at the beginning, that limit information, it turns out, was exactly enough for us because all we're told about our region is that it has an area of 6. Also specifically that our curve C was positively oriented. That was important for us, but it just means that Green's theorem can apply directly. We don't need to do any extra steps to apply Green's theorem. If we were told C was negatively oriented instead, all the work would be pretty much exactly the same. The only difference is that because we had a negative orientation, we'd multiply our answer by -1. But again, we saw that our region has an area of 6, which means that if I integrate dA, I'm going to get 6. And then negative 9 times 6 is negative 54. As long as I remember my simple arithmetic, all right, which is never a given with me, but pretty sure 9 times 6 is 54. Cool. So negative 54, the whole thing. All right, so got you started with an easy one in Green's theorem. Let's look at how about a medium one in Green's theorem? So here we go, the real fun stuff in the post-exam 3 content. Use Green's theorem to find the work done by the force field given here, capital F, in moving a particle along the x-axis from point to point and then back to the original y-axis. So, highlight a couple of things here. It says use Green's theorem to evaluate the work done. So, if we go to our formula for work, this one is, if you've taken a physics course before, this one will feel a lot more familiar or comfortable from that perspective than necessarily from a purely calculus perspective. But work done is equal to the integral of f dot dr along the path, or what we'll call the curve, c. And that's the calculus definition for work, as opposed to maybe the original definition for work that just is algebra based, which is just force times distance. Turns out we have to be a little more sophisticated with that work formula if we have a variable force instead of a constant force. A lot of times we end up looking at variable forces, like we have with this particular force field F here. But work is the integral of F dot dr. So the best hint I can give you for getting through a Green's theorem or a Stark's theorem or a divergence theorem problem is that when you encounter one of these things, it'll say use blank theorem to solve this integral. And the integral provided to you is not the integral you should do. So this one is saying use Green's theorem to evaluate this line integral. The hint here is do not do that line integral. Whichever one the question tells you to do, you should use Green's theorem to do the opposite side of the equal sign. So because I'm being told to do the line integral, I'm thinking in my head, okay, I should really be doing the double integral over the region. So that's my super secret hint for solving any one of these problems. Don't do the one that's provided to you. Granted, this particular web work problem is guiding us through it a little bit more. So it is setting up the other half of Green's theorem for us. The double integral part is what we want to do. But the statement is telling us, hey, do the line integral, and we gotta go, I'm gonna do the other side. Chances are it's like 10 times easier to do the other side. And since we're kind of picking out specific functions for a math exam, it'll work out to be that the other way is easier. So if I wanted to put together what it was that I was doing here, because that will be a bit important to us, we're going from the origin to 4, 0, along the line segment that goes up to 0, 4, and then back to the origin. So if I were to draw that in, I'll need some coordinate axes. So I'll plot them real quick. And what are we doing? I need to label some things along the axes. I want a 4 here. I want a 4 there. I'm going to start at the origin. I'm going to go to 4, 0. I'm going to go to 0, 4, and then I'm going to return to the origin. So my path is going to look like this. Going first this way, then up that way, and then back down this way. Not exactly drawn to scale, is it? But oh well. What you're gonna do? Actually, clean this line up a little bit. Okay, cool. So that is the path we're supposed to take, and it's a closed loop. So it defines this nice looking region on the inside. So even with the formula I had drawn up down at the bottom, I've got my work, which is the line integral along the boundary curve C drawn in blue. Green's theorem tells me that it's equal to the double integral over the region D, so that green region that I drew in. Green for Green's theorem. It's okay. I should just stop and actually do the math over here. Okay. Right. Uh, so if I were going to do this the line integral way, I would parameterize each of my three boundary curves, which are just three lines, one that moves between every pair of points. Parameterize each thing, do a separate line integral over each of those three boundary lines, add them all up, I get my work solution. So that's the straightforward way. The Green's theorem way is saying, okay, I don't want to parameterize three separate boundary lines. I'd rather just do a double integral over this nicely defined region that I've got in front of me, because that region's just a triangle. I know I could do an integral over that relatively painlessly. So that's what I'm going to do. In order to do that, I'm going to need an equation for each of my bounds. So this diagonal line up here, y equals 4 minus x. If I'm going from 0, 4 to 4, 0, or the reverse, just, get the equation of a line that contains those 2 points, I believe you'll find y equals 4 minus x. And then, of course, we've also got y equals 0 here and x equals 0 being the other guy. But if we're going to put all our bounds together, the fun one is our upper bound for y. It looks like this integral is being set up to do y first. We could probably get away with doing either one first, but we're doing y first, so we'll do it that way. The upper y bound is 4 minus x. The rest of them are pretty straightforward. Our lower bound for y is 0, then x being second just goes between a couple numbers. X is between 0 and 4. So those are going to be our bounds. Then the last piece that we need to set this thing up is the actual integrand itself. So let me come back up and label my P and my Q. Those are important, my X component and my Y component. And take a couple derivatives. I want to start off with Q partial X, which is just Y squared, minus, I need P partial Y, I need the other one. So P partial Y looks like I should distribute that stuff through. I'll get negative 6x, negative 6x squared minus 2xy, do a Y partial, and I'm going to get negative 2x. Let me switch back over to purple here. Negative 2x times 1. I suppose, yeah, I could have just done that as a, it's actually not bad as a, don't even really need to distribute because the 2x I can just pretend is a constant. So just take the derivative of the inside, it's 1. Yeah. Either way, I don't need to get too intense on how I'm going to set up uh, that particular derivative. So now that we're all set up, I think we're ready to calculate something. So I've got a double integral here of y squared plus 2x. And I'm doing dy first. Let me save that for the next step, actually. We'll just continue leaving this as dA over the region D, one step at a time. And just like Johnny Cash said. So that means then I'll set up, change my double integral to an iterated integral of y squared plus 2x dy is going to be first. Y goes from 0 to 4 minus x. And then dx is second. X goes from 0 to 4. So all I got to do now is evaluate this thing. So this will be now the single integral. The single integral. I'm going to do the y integral. Yeah, just evaluating this thing. I'm going to get y cubed over 3. So this will be 4 minus x cubed over 3 plus 2x times 4 minus x minus the evaluation when I plug in 0, but I'll just get 0 when I do that. Leaving me with a dx token, x still goes from 0 to 4. All right, so let's integrate this thing. And hopefully we'll integrate it the smartest way we can think of. Let's see, that's going to integrate to 4 minus x to the 4th over 3 times 4. And then I'll also need a -1 for the reverse chain rule or a u substitution, depending on how you want to think about it. You could also cube that thing out if you wanted to, but I don't want to cube that thing out, so I ain't gonna. Again, thing I got 1 over -1 over 3 times 4, so I'll simplify to -1 over 12 times 4 minus x to the 4th power plus doing the rest of that stuff together. 2x times 4 is 8x. 8x integrates to 4x squared. And then on the other side, 2x times -x, that'll get me -2x squared, which will integrate to -2 over 3x cubed. And then this thing, I want to evaluate between 0 and 4. We'll plug that in, see what we get. I'm just going to spare this extra step. I got 128 over 3 because I did this one out ahead of time. But the plugins aren't too bad. Plug in 4, the first term is 0. 4 times 4 squared, that's going to be 64. Yeah, it's a calculator problem from there. So I'll let you double check that if you want to. I got 128 over 3 when I did it. All right. And up next, I thought I'd review a question from quiz 9. Still pertaining to Green's theorem here. So we'll consider a curve C. They gave us a parameterization. We want to find the work done by the force field F and moving a particle along C. So again, this question is basically telling you, here's a parameterization, here's a force field, find the work done, which means do the line integral, right? It's what the problem's telling us to do. It's telling us, hey, do this line integral. And whenever we see a Green's theorem problem, whatever thing they tell us to do is not the actual work we should do. It's telling us to do a line integral. So we should think, okay, told me to do a line integral, I should instead do the double integral. So that's exactly what I'm going to do. Skip that line integral business. I'm just going to move directly over to the right side and hopefully see some things work out all right. Yes, this is Green's theorem. Make a green equal sign for Green's theorem. So I want to do the other side. I don't want to bother using that parameterization. That force field looks awful. I don't want to evaluate along it. E to the negative x cosine of y cubed. Yuck. So I do the other side instead and hope something nice works out. So I'm going to switch this thing over to the double integral of q dx is just going to be -4 minus p dy. Well, that's just going to be 8 dA over my region D. That double integral looks way nicer than whatever I was going to get if I parameterize and do some awful stuff on the left side. So with all that together, -4 minus 8 is -12. I'm just going to factor that out. So I just have the double integral over the region D of the integration token dA, which means that double integral of dA is just the area of my region. So now I am going to look back up at the parameterization because it will be important to tell me what my shape looks like. But this is one we've seen before. It's very, very similar to polar coordinates. 4 cosine t for x, 4 cosine t for y, or 4 sine t for y. T being our analog for theta is going between 0 and 2 pi. So I want the full circle. This thing must be a circle with a radius of 4. So the area is pi times r squared. And again, based on my parameterization, that radius must be 4. Put it all on screen for a second. And from there, just got to multiply some numbers together. 4 squared is 16. 16 times 12 is 192. It's a negative 192 pi. All right. Then we'll take a quick backtrack to chapter 15 to look at surface area. We pulled this one out of the exam 3 content and instead moved it into the post-exam 3 content because it relates more to the surface integrals that we're going to do right after this problem. So we'll just need to remember a formula for surface area. There are several out there that are geometric formulas for surface areas if we've got a well-defined shape. But the generic calculus one looks like this. Surface area, well, it's an area, so it's going to be a double integral. So I'm going to want the double integral over some surface S. Difference between a surface and a region, that a region is a flat 2D shape in 2 space, a surface is a curved or wavy 2D shape in 3 space. But we want to take the double integral over the surface of a handy looking formula. I want z partial x squared plus z partial y squared plus z partial z squared, which is just 1 squared, ds. D big S or D little s? This must be D big S. Yeah. I mean, that's just, pedantic, uh, deciding between the two. There's a particular reason for it, but you don't have to worry about it. Not right now, because we've got plenty of other stuff that's going on. So this formula then works out, the one that we have here specifically is going to work if we can write z as a function of x and y. But as it turns out, that's already done for us. We're given z right over here. It's a paraboloid. It's 16 minus 3x squared minus 3y squared. So what do we want to do? We should, oh, it's above the xy plane. I suppose that's important for us too. But that'll be important when we're setting the bounds. Right now, we know that this is the surface that we want the surface area of, right? So we want the surface area of this paraboloid, which means that's the function that we should be using to create the integrand for our surface area integral. So whatever surface I have, that's what z needs to be. So I'm going to plug that thing into the formula, but where that thing comes from, or maybe a slightly more recognizable version, now that we're to the point that we've seen surface integrals, that thing on the inside, that square root that we're integrating, is really the magnitude of a particular vector. That vector being negative z partial x, negative z partial y, and 1. Which is just going to be the normal vector along our surface, which is why we moved surface area, which is a chapter 15 concept, out of the exam 3 stuff and into this post-exam 3 content, so we could really relate this idea right here. The magnitude of this normal vector that we see a lot when we do surface integrals, and then again later on in Stokes and the divergence theorem. So if we calculate that magnitude, we'll see that it is exactly that square root written up in the formula above. Z partial x squared plus z partial y squared plus z partial z squared. But that's really just 1 squared. Derivative of z with respect to itself is 1. So let's just simplify that thing. If we do, what do we get? Yeah, let's try again. Z partial x, that's going to be negative 6x squared plus z partial y, that'll be negative 6y squared plus 1 make my square just a little bit longer. And I can simplify this thing a little bit. 36x squared plus 36y squared. I can already see I'm changing this thing over to polar coordinates because it's going to be way easier to integrate over there. All right, I've got this paraboloid that has circular cross sections. I want to do a polar integration. So I'm going to say x squared plus y squared is r squared. So this thing simplifies to 36 r squared. plus 1. And this whole piece that we've been doing so far, that's what we want to go in here. With a little bit of extra, because we're also going to need to multiply by r. Since we need to convert our dA integration token or ds integration token over to polar coordinates as well. So, yeah. Yep, that's our plan. So that maybe have actually been a dA back up at the beginning. I think it should have. Because I've already converted to x and y. Yeah, that should be dA. I'm already making that into a region. I have it in my notes to be ds. I might have to check that later. Okay. Again, I'm talking about things that aren't all that terribly important at present. So I need to set up some bounds for this integration. This surface area. Just write out the integral for us real quick. Surface area that we want is going to be the double integral of that thing we just found. Square root of 36r squared plus 1 times r dr d theta where theta, so the integral I set up for my outside, let's put it in green. I'm going all the way around my circle, so it's 0 to 2 pi. Right, we're not stopping anywhere in that direction. The place where we need to stop is the xy plane. So I'll need to look at the projection of my paraboloid down into that xy plane, which, as it turns out, that projection is just going to be when z is equal to 0. So I'll want 0 equals 16 minus 3r squared. Yeah, I can do it in blue, that's fine. Solve that thing for r. And I'm just going to pick the positive value out of the square root right away. No need to mess around with the plus or minus right here. Square root of 16 over 3. Let's call it 4 over square root 3. So our bounds for the radius, I want to start from the middle, so 0, and go out to 4 over square root 3. That's the integral that I'd like to do here. Right, let's turn that guy blue too, just to emphasize everything that we're doing over here. So let's do this integral, or this iterated integral. Let's notice first that our bounds are just depicting a polar rectangle, meaning that our bounds are just constant numbers. Our function is separable because there aren't any thetas in it, so there's only d theta. So we can split up this double integral into 2 separate integrals and multiply them together. Going back to Fubini's theorem from way, way back at the beginning of the course. I say way, way back. That was only like 5 weeks ago. Man, the summer is fast. Okay, so our theta integral is just going to come out to 2 pi. Then I want to integrate the rest of that thing. I'd probably pick a u substitution that's 36r squared plus 1 is u, means dr is going to be 72r. The r is already there, but it is missing that factor of 72. So I'm going to multiply it in right here, 1 over 72. Cool. That sets up our U substitution for us. So we just have to integrate that thing. We're gonna integrate a square root, which has a power of 1/2. It'll integrate to a 3/2 power. So if I integrate up to 3/2, I then need to divide by 3/2, which means multiplying by 2/3. So multiply that guy in right there. And then everything on the inside is just what happens when I evaluate that square root. The first time through, I'll get 36 times 4 over the square root of 3 squared plus 1. Close that parenthesis because that's closing the inside of the square root. The thing is now to the 3/2 power minus, what do I get when I plug in 0? I get I'm going to get 0 plus 1, which is just 1, to the 3/2 power, which is still 1. So that's my integration right there. Works out to that. I'm going to leave it there rather than simplifying that algebraic mess. Because I don't want to. That looks ugly. So it's going to stay just like that. One of the things I didn't write down over here, dA was r dr d theta. One of the important things that we need to remember from back when we did integration in polar coordinates, changing our integration token into polar. I guess it's probably not the end of the world. No, that's not going to come out to anything nice. All right. There's a surface area. Let's do Stokes' theorem. So the second of the 3 major theorems we got going on in this review set. So once again, probably same idea is going to apply. Whatever thing we tell you to evaluate, you should do the opposite. So this thing says use Stokes' theorem to evaluate the flux of the curl of F. Yeah, that should be the flux of curl F. Either way, it's the double integral along the surface S of the curl of F dot ds. We told you to do the double integral, so you should think in your head, I don't want to do that. I'm going to instead use Stokes' theorem to switch it to its other side. Instead of doing a double integral, I'm going to do a line integral along the boundary curve C of F dot dr. Cool. So that's going to be my plan. Whatever they told me to do, I'm going to do the opposite. So what do we have going on? We've got some field F. It's got a lot going on. S, our surface, is the hemisphere. X squared plus y squared plus 1, x squared plus y squared plus z squared equals 1. With the inequality z is greater than or equal to 0. So we have the unit sphere being sphere, radius of 1, centered at the origin. That's what that first equation is telling us. It says it's a hemisphere, specifically with z being greater than or equal to 0. So we're looking at the top half of this unit sphere. So what do we want to do? Definitely want to highlight this part right there. Z is greater than or equal to 0. That's our hemisphere. And what do we say over here? Since our hemisphere is oriented upwards, the boundary curve must be traversed blank when viewed from above. So it's important when we set up these Green's theorem and Stokes theorems problems, Green's theorem and Stokes theorem problems, even the divergence theorem, we're going to be working with some vectors, and it'll all end up being important that these vectors have the correct orientation. we are, anytime we want to apply the theorem directly, the theorem is going to be assuming a positive orientation. So if we want to use the theorem, we just need to make sure that we've got our positive orientation going on. So if we're viewing this thing from above, we're viewing this thing from above, the positive orientation for traversing a curve is counterclockwise. So I'm just going to write in CCW for counterclockwise. I believe it'll write out the whole thing if you look at the drop-down tab, but CCW for me, counterclockwise. That's our positive orientation. And if we're going to do that, we'll also want to parameterize our boundary curve. So if we're talking about this hemisphere, it's just the top half of that unit sphere. So we're cutting it off in the XY plane, which means that our boundary curve for this surface is that circle in the XY plane. So I'm basically just parameterizing the unit circle because this sphere had a radius of 1. You can see the way WebWorks set it up. If you had a different problem, you might have had a different radius, but mine's 1. So X it's giving me is 1 cosine t. That means that Y is going to be 1 times sine t. Again, I'll write in the 1 just to emphasize that, if we needed a radius in there, we could multiply it in. And this circle is in the XY plane because that's where we're cutting off our unit sphere. So the Z component of this boundary curve is 0. Again, that's because we're in the XY plane. We're going all the way around our curve, that boundary curve, which is the circle. So theta, or t, should go between 0 and 2 pi. Again, had no reason to restrict theta, so I'll just assume it's 0 to 2 pi. The restriction that we had was on z to get that hemisphere, but that doesn't impact theta. Theta is still 0 to 2 pi. I want to go all the way around. Cool. So we're basically ready to integrate this thing. Only thing we're missing is dr. So I'll calculate that. Dr is going to need the r prime vector. So let's calculate r prime of t. And it is derivative of cosine, which is negative sine. And then in the y position, I'm going to need the derivative of sine, which is positive cosine. And then the derivative of 0, which is still 0. Kind of it to work out that way. So let's set up this integral. I'm saying that Stokes theorem. S for Stokes. It's actually S for surface, but it's kind of funny it works out that way. The surface integral of the curl of f dot ds is equal to the line integral along the closed boundary curve C of our regular field f dot dr, which is going to be the single integral of our field. Should write that down while it's still just barely on the screen. Right up here at the top, that's our field. I've got 7y, which is going to be 7 sine t, times the cosine of z. Z we know to be 0 along our boundary curve, and the cosine of 0 is 1. Cool, that's our x coordinate. Up next, 2e to the x times the sine of z. Again, z is still 0, we're on our boundary curve, and the sine of 0 is 0. So this whole middle term, this whole middle coordinate component, there it is 0. Then up next, The last one's ugly, but fortunately our prime is going to come in and save us. But let's just write it out for now. 3x is 3 cosine t e to the y, which is sine t. All right, cool. That's our field F all written in. I want the dot product with dr, which is r prime dt. So negative sine t, positive cosine t, and 0 dt, where t we knew from above bounces between 0 and 2 pi. So like we set up that whole integral. So now we can evaluate it. Or we'll evaluate it. We're not quite ready to evaluate it. First, I want to simplify that dot product. It has a super nice simplification. It is nice because the rest of the problem's a bear. But once we actually take our dot product, it's so nice. All that survives is our x coordinate, because the y coordinate gets multiplied by 0, the z component gets multiplied by 0. So I'm going to get negative 7 sine squared of t dt integrated from 0 to 2 pi. A few different options for evaluating this integral. My favorite is to say that sine squared, if I integrate it over its full period, well, I know that sine squared and cosine squared, when added together, get me a rectangle that has a height of 1 and a width of 2 pi. They stack on each other very nicely. And those functions are symmetric to each other, or they have a certain symmetry to them, meaning that within that rectangle, half of the area comes from the sine squared function, half of the area comes from the cosine squared function, meaning the integral of sine squared over its full period is half of that rectangle. Again, that rectangle had a height of 1 and a width of 2 pi, so half of that area is just pi. So I end up getting that. And I know I just talked about a bunch of stuff there. You're probably thinking, what? And yeah, I've got a diagram I could bring in here. So bear with me just another second. Here we go. Grab this thing from our polar coordinates integration section. Scroll down to the problem we are currently working on. Yeah, paste me right here. Okay, here's the geometric idea that I used to calculate this integral quickly. So I'm just looking at the sketch of the region that's down here. I've got sine squared is the function that's drawn in sort of the darker line in the middle. But that means that the function above is 1 minus cosine squared. And because of their particular symmetry, and also the trig identity that relates sine squared and cosine squared together, if I stack them nicely, they just make a rectangle when I graph them together. Now, if I add them up, all I get is 1. So I'm just integrating out along a certain way. And there are a few points of symmetry that show up within this rectangle. 2 pi, pi, or even pi over 2, I could split them up there to find nice looking symmetries. But since we got 2 pi, that's the easiest one. It's that whole rectangle has a width of 2 pi and a height of 1. And both the sine squared and the cosine squared function are symmetric within that. So sine squared makes up exactly half of the area of that rectangle, as long as I stop at a convenient spot, 2 pi being one of those convenient places. So it's half of the area of this rectangle. Area of the whole rectangle is 2 pi. So half of that is pi. And that works whether I'm integrating sine squared or cosine squared. As long as I'm integrating over a full period, the area comes out to exactly half of the rectangle. And again, that'll still work at a couple other nice breakpoints. I could stop it at pi, and I'll still have symmetry. I could stop it at pi over 2 even, and I'll still have symmetry. But anything beyond like those points or their coterminal angles, the symmetry doesn't work quite as nice. But this one was nice enough, so I used this fancy integral shortcut. It's my favorite for evaluating a sine squared function. Alternatively, you could use the double angle formula. Yeah, that's the one. Double angle formula to change sine squared to like 1 minus cosine 2 theta, or 1 minus 2 cosine 2 theta all over 2. Yeah, 1 minus 2 cosine theta over 2. I think I threw an extra factor of 2 in there that I didn't need. But I could do it that way and then integrate that thing. But I'd get the same answer. Geometrically, it's much cleaner. So I like to use that wherever I can. All right. Hopefully you liked that problem. We've got another one. This one's even starred. So I must have been making a note to myself when I put a star on this problem, which means I think that this one is particularly important to look at before taking the final. So if you're going to spend extra time on any of the problems in this review, I think this is the one to do it on. I think that's what that star means. At least if I know past me well enough. So, previous problem, it said use Stokes' theorem to evaluate this, double integral of the curl. This time it says use Stokes' theorem to evaluate the line integral. So, since it said evaluate the line integral, you should be thinking to yourself, baby, we should do the double integral instead, which means we are going to want the curl this time, and we're going to need, a few other things that go into it. Means we probably also want to figure out what our shape looks like. But enough of that. Let's go through this problem. We're given a force field F. It's there. I'll come to it when I need it. It tells us what our curve is. It's a triangle that bounces between the vertices 3, 0, 0, 0, 3, 0, and 0, 0, 3. And it's oriented counterclockwise as viewed from above. Since the triangle is oriented counterclockwise as viewed from above, the surface we attach to the triangle is oriented upwards. Oh boy. Okay, my electronic pen is leaking ink, if you can believe it. Right. Just turn it off and on again. Pretty sure that's how you fix a leaky pen. Upwards. Yeah. It's clean now. Okay. So yeah, and again, we knew that from the counterclockwise viewed from above section. That told us we were doing an upward thing. All right. So we've got that part together. Let's calculate the curl later. First, we know if we're going to be doing the other half of Stokes' theorem. Excuse me. We know if we're going to be doing the other half of Stokes' theorem. In addition to the curl, which we can calculate in a minute, we're also going to want a normal vector. So I want to calculate that normal vector. In order to get the normal vector, I think I'll first need to know what my surface looks like, which means I should go look at my surface. I know it's a triangle. It connects three vertices. So while the surface is a triangle, it exists in some plane. So I want the equation of that plane. That's my goal here. So if I want to get the equation of a plane, I'm going to need to calculate a normal vector, which means I need to use the points provided to calculate a normal vector. You might also notice that we're really doing this so that we can get a normal vector, and now we're going to get one in order to calculate the equation of a plane, which means there's a fancy side or a fancy shortcut we could use if we really wanted to. But let's not do that just yet. Okay. Calculate a normal vector here. So the normal vector that I'll do, let's do 3, 0, -3 cross 3, -3, 0. So all I had to do was take my 3 points and find vectors that connect two pairs of them. So what I chose to do was to connect my second 2 points to the first one. So 3, 0, 0 minus 0, 0, 3, and then 3, 0, 0 minus 0, 3, 0. That's where I came up with that. Take a cross product here. You should hopefully get 9, 9, 9. Yeah, that's what I get when I do my cross product here. Then set up the equation of a plane based on our normal vector. I'll have 9 times x minus, how about x minus 0, plus 9 times y minus 0, plus 9 times z minus 3. All that is equal to 0. So I just have to pick the equation or pick one of my points and plug it into the equation of this normal vector, or plug it into the equation of this plane, right? And the plane uses a normal vector and a point. I chose the last one, 0, 0, 3. You could have chosen any one of the three, just like you could have done slightly different vectors in the cross product. You'll get either 999 or -999. Either one is fine. Because we'll make a choice on our orientation later. We just need to get a normal vector first. So I plug everything in up here. I want to solve this equation for z. So that's what I'm going to do. Divide everything by 9. Those can all go away. And z is equal to 3 minus x minus y. Oh yeah, cool. So we got the equation of our plane. Now we need our normal vector. I'm going to put it in green because I've said that I wanted my positively oriented normal vector. And for the particular normal vector that I wanted, I know it should be z partial x, z partial y, and then 1. But in order to have this thing be positively oriented, I need the z component to be +1. Or rather, I need the z component to be positive because my positive orientation is upwards. Anytime we talk about upwards in 3 space, we're talking about our z component. So the z component of our normal vector should be positive, meaning the normal vector is really negative partial x, negative partial y, positive 1. As a quick aside, um, the other option for our normal vector could have been z partial x, z partial x, z partial y, negative 1. And that's our if our curve were oriented clockwise, we would have chosen this normal vector instead because we would have wanted the downward orientation. I'm going to gray that out because it's more of just a bonus part here. But again, the parts that end up being important here are those elements in red. If it's downward, that means the z component should be negative. But we didn't want that. We wanted the positively oriented one. So if we actually calculate this thing, it's going to be negative z partial x, which is negative 1. Then negative z partial y, which is also negative 1. And finally, 1, or z partial z, which simplifies to 1, 1, 1. Super nice normal vector. All right, so we've got our normal vector. We made sure we had the correct orientation for our normal vector, which is also important. And then let's take that and bring this problem home. So we still need the curl. Haven't calculated that yet. So give me curl F. I'm going to come up and draw some color into our field. I'm going to give the x coordinate's going to be purple, the y coordinate's going to be yellow, the z coordinate's going to be magenta. Help me keep track of what I'm doing. So my curl should be magenta partial y, which is 0, minus yellow partial z, which is 2z. Then up next, I'm going to want purple partial z, which is 0, minus magenta partial x. Magenta partial x is going to be 2x. And then finally, I'm going to want yellow partial x, which is 0, minus purple partial y, which is 2y. Cool. So there's my curl. I should clean that up a little bit because I know I'm going to have to work with it. It's negative 2z, negative 2x, negative 2y. All right, we've got our curl, we've got our normal vector. We're so close. Let's just state one more time what it is that we're doing. We're supposed to be evaluating the integral of f dot dr along the closed boundary curve C of the surface S. And Stokes' theorem coming in clutch, telling us that instead of evaluating that line integral, we can instead evaluate the surface integral of the curl of F dotted with ds. And one more simplification. really emphasize what we wanted to do here, because that is the statement of Stokes' theorem, but then we've got a slight little alteration we're making for the sake of an easier calculation. We're going to say that that vector valued ds is really a normal vector times the regular scalar integrator token ds. That's what we want to do. So what we need the curl dotted with the normal vector, and then we can have our, basically our regular old dA is going to be coming in. So we've got all that. Let's just write everything in. I've got an integral of curl f dotted with n. So this thing looks like negative 2 times z, but now we're doing a double integral here, or an iterated integral. So we want to make substitutions for z, because, well, really we need to parameterize this surface with our two parameterizing variables, or our two parameters, u and v, or r and s, or da 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 da. But like, we can skip over that step because we've already basically parameterized this thing because we've got z as a function of x and y. So I'm going to keep x and y as my two parameters and replace z with it. No need to go on an extra parameterization crusade if we don't need to. So z from up at the beginning, this guy right here, we got that z is 3 minus x minus y. We needed the equation of our plane. So we're going to substitute that into the curl right here. Then the rest of it was a negative 2x was right there. A negative, got a comma, a negative 2y is right there. Dot this thing with a normal vector, which we got was 1, 1, 1. And then I'm just going to slap a dA right there. Yeah, yeah. So I need to claim what this thing is integrating over. We've now done a parameterization here without really mentioning it. So this is a two-dimensional region D instead of a surface. I'm going to call it D there. But really D is like basically S. It's just in 2 space now instead of 3 space. It's going to be the projection down in the XY plane. So clean up this dot product. I'm going to have a negative 6 plus 2y plus 2x minus 2x minus 2y. The only thing that survives out of all that is a negative 6. So we're looking at the double integral over the region D of negative 6 dA. Cool. So all that means then is we need negative 6 times the area of our region. We know that this region projected down into the XY plane, which is where our parameters exist, is going to be a triangle. And I think we saw back at the beginning, 3, 0, 0, 0, 3, 0, 0, 0, 3, project that down in the XY plane, and we've still got a triangle where our base and our height are both 3. Cool. So clean that up. 1/2 times 6 is 3. 3 times 3 times 3 is 27. So negative 27. Cool. So again, I think I starred this problem for a reason, which means I think this one in particular is one that you'll want to pay attention to before you take that final exam. So be get yourself to a point where you're as comfortable as you can be with this problem before you click that final button. And now that we did that, I think we only got one bit left, the divergence theorem. I've got a few more problems I want to talk about, but this is our last big thing. We got a divergence theorem. Let's see what the heck goes on. So what do we get? We get the whole problem on the screen. So we want to use the divergence theorem to calculate the outward flux across the S, which is the surface of the solid, bounded by y squared plus z squared equals 25. So that's a cylinder that's got, circular bases or circular cross sections, and two planes, x equals 0 and x equals 4. So we're going to set this thing up and then we're going to knock it down. So the divergence theorem, that's the one that says that the outward flux, which is a double integral through the surface of a solid, that double integral is going to be equal to the triple integral of the divergence of the function. And, again, we do whichever thing the problem didn't tell us to do. So even though it sets up the triple integral for us, it was telling us to do a double integral. It's telling us that with its words. So it says calculate the flux. That flux is a double integral through a surface. All right, a surface integral. And we're going to change it over to a triple integral using the divergence theorem. That's my great plan here. So let's start trying to set some things up. X is going to go between 0 and 4. And then y and z, we go just look at our order real quick. Tells us to do z first, and then y, and then x. So we're going to need to use the equation of that cylinder right here to get our bounds for both y and z. So y gets to go second, so it's easy. It's just -5 to 5 because the radius of those circles is going to be 5. Z's got to go first, so I've got to solve that equation for z. We're doing, we're going around this whole surface here. So the whole circle's fair game. So z should just bounce back and forth between the positive and negative square roots. So negative square root 25 minus y squared. Should zoom in a little bit so we can write a little more clearly. 25 minus y squared and square root 25 minus y squared. These parts aren't like super important here, these bounds, because we're not actually going to use them. This integral is clearly asking us to set up a cylindrical coordinates problem. So before we actually do any integration, we're going to bail on this setup that it asked for anyway, because we'd much rather be in cylindrical coordinates. I mean, it told us like, hey, one of your shapes is a cylinder. So we're not going to do that. Bring that over here. So that's where we're grabbing those bounds from. But again, don't super care about them. We're not using them anyway. I mean, X will stay, but Y and Z we're going to change. So We decided that instead of calculating the flex as a surface integral, we want to use the divergence theorem to do the triple integral of, surprise, the divergence. It's funny where it gets its name. So we need the divergence of f. So all the way back to the very first problem we did in this review, divergence of f. Divergence of f. Divergence of f. There we go. That is the del operator dotted with a vector field f, which means we just take our partial derivatives right down the line and add them up. So dot product with that partial derivative operator. Going through derivative of our first piece. I'll color code these guys again as well. Purple piece, a yellow piece, a magenta piece. We need the derivative of the x component, which is 6y squared, plus a derivative of the y component. Y component has no dependency on y, though, so its divergence is 0, or its piece of the divergence is 0. And then finally, 2z cubed. That thing is going to have a partial derivative of 6z squared. So I'm going to take this guy right here, draw a whole bunch of arrows around because he goes all the way back up there. That's our integrand. We just want to integrate the divergence of f. And hey, just like that, we've got our whole thing basically set up. And I'm going to breeze through the rest of the problem, if that's all right. From here, it's just going to be a double integral calculation in polar coordinates. So in the interest of time, I did this one ahead of time. So divergence theorem tells us that the flux integral, which is a surface integral through the surface of our solid. Again, notice I've got the special notation going on in here. Doesn't mean anything in terms of the calculation. It's just indicating that circle there on the flux integral. Could probably like use an arrow to point what I'm talking about here. Talking about up here, that circle that goes through the double integral on the flux integration. That circle is just there to indicate that our surface S is closed. So we're integrating over a closed surface, which is important because in order to apply the divergence theorem, we have to have a closed surface, because closed surface is what we need to define a solid. But yeah, circle there just tells, hey, look, this surface is closed, just so you know. That's all it's saying. And we can say that that closed surface integral is equal to the triple integral over the solid that is contained within that closed surface. And instead of just doing a straight triple integral of the field, we need a triple integral of the divergence of the field. And then we just have a dv volume indicator, or a dv integration token that we'll be spending. I went ahead and wrote out the one in rectangular coordinates because the problem did ask for it to be set up that way. But I mentioned when we were going through it that no, we're integrating a cylinder. Let's integrate in cylindrical coordinates. It'll be much nicer for us. So I'm just going to go ahead and use the cylindrical conversion over on the left, the one that's highlighted in pink. Traditionally, our cylindrical coordinates extend up along the z-axis, but this one just was rotated so that it extends along the x-axis instead. So we'll just write a new cylindrical coordinate conversion that is basically that. So x will stay x instead of z staying z staying z. So I'll change y and z over to r cosine and r sine theta. It doesn't really matter which one I put where. It should be fine either way. But I went with just shifting everything, down the order. So y is now r cosine theta, z is now r sine theta. But again, shouldn't actually matter which one we pick. because of the symmetry that this shape's got going on. I mean, that's why we wanted to do cylindrical coordinates, is specifically because of the symmetry that it had. And then the thing that we're integrating, I'll first simplify it to 6r squared times cosine squared plus sine squared times r dr d theta dx. Remember that we need that r in there for when we change over that dv integration token. So that's the determinant of the Jacobian, which we only very briefly talked about in an announcement, or if you watched the video on change of variables, which was not necessary, but that is where we talk about what a Jacobian is. Simplify that thing a little bit. It's 6r cubed times dr d theta dx. Perfectly separable triple integral. So I'll do an x integral, a theta integral, and an r integral. X integrates to 4, theta integrates to 2 pi. R, we get a 6r to the 4th over 4, integrating between 0 and 5. So 12 pi times 5 to the 4th, which is 7,500 pi. Cool. At this point, it's, that's just a triple integral that we're falling back on there. The big thing that we want to focus on in the divergence theorem, which even though it's last, probably ends up being the easiest of the three new theorems, is just that we can set a flux integral equal to a triple integral through the solid of the divergence of whatever field that we were into. Ooh, cool. All right. So that's our divergence theorem. Probably look at another one here. Ooh, and it's I left one more to be done together, it seems. Or at least part of it together. Because again, I think I just want to be setting up this integral. Yeah, so it looks like I'm gonna do just this first part. Oh, I've got most of it done out already. Okay, so it seems like the thing that I wanted to focus on mostly, as far as like, the setup that you want to be here for, is setting up one of these problems. So this one is asking us to, it's problem 1 in the divergence theorem, which means it's asking us to do both sides of the divergence theorem and just verify that we get the same answer. So it looks like what I wanted to do was just do the first step together and then show you that, hey, look, I verified the other half. So we're going to set up the triple integral side and see where it gets us. So oh no, my pen decided that it needed to be reset. So I just turn it off and on again, which means pulling out its battery. And what do we get? We need the divergence of F. So F is this field up here at the top, vector field. So it's got its 3 components. I want the divergence, which means let's take partial derivatives right down the line. The derivative of 2x squared is 4x. Oops. Purple, please. 4x with the derivative of 2x squared. Derivative of 2xy with respect to y is going to be 2x. And up last, derivative of 3z is 3. So that's our divergence. And then the integrand that goes into the divergence theorem triple integral is the divergence. So I'm going to clean it up and call it 6x plus 3, so I can combine some like terms. That's the thing I want to be integrating. Wants us to set up bounds again. So let's see what we've got. We are integrating a paraboloid. And if we look at our bounds real quick, it says do z first, then do y, then do x. So our solid is going to be bounded by the paraboloid 25 minus x squared minus y squared and the xz plane, which is the plane z equals 0. So our z bounds are 0 and 25 minus x squared minus y squared. Project that thing down the xy plane, doing z equals 0. We get the circle, x squared plus y squared equals 25. Which means we're almost certainly doing this integral in cylindrical coordinates again, instead of in the rectangular coordinates that we're asked to set up. But we'll still oblige web work and get the bounds set up. But then when I actually do the work, like, I'm gonna ignore it and do it my own way. So my y bounds need to be between the positive and negative square roots of 25 minus x squared. That means my radius is 5. So x will bounce back and forth between -5 and 5. That's what they wanted us to set up. But again, we're not actually going to do that integral because why? That looks bad. So over here, I already took the liberty of converting this thing over to cylindrical coordinates and integrating it that way. So instead of, this one is just a straight conversion to cylindrical coordinates. Z gets to still be Z. So x will be r cosine theta, y will be r sine theta. Our dv token is r dz dr d theta. Told us to do z first, so we'll keep z first in our order. Z is still 0 to 25 minus r squared now. And then, we have a circle radius of 5, so we integrate from 0 to 5. We want the full circle, so theta is 0 to 2 pi. I integrated that thing and got 3 pi times 25 squared over 2. And that's probably all we need to do there. So that means I'll just plug this in over here. We found 3 pi times 25 squared. Wait a minute. Yeah, 25 squared over 2. Just plug that in there. So the rest of the problem, I just kind of want to talk about conceptually. So what the rest of it is saying is that I want to directly calculate the flux that goes out of this solid, which means I'm going to want the flux of, I want to the flux through all of its surfaces. And if we think about the way we're constructing this solid, it has 2 surfaces or 2 faces that I really want to consider. It's got the paraboloid that's defined there at the beginning, z equals x squared, z equals 25 minus x squared minus y squared. That's our paraboloid. The other face or the other surface this thing has is the disk down in the bottom, the disk that's in the xy plane. That's just that circle with a radius of 5 centered at the origin. So if I wanted to calculate the total flux out of this solid, I'll need to calculate the flux that goes through both of those surfaces. So I'll have one that's a paraboloid, one that's flux through a paraboloid, and one that is flux through a disk. And I can use some fanciness to calculate the integral of that flux that goes through the paraboloid. Because as it turns out, trying to set up that integral is a little tricky. I mean, I think we'll look at doing it anyway. But an easy way to just jump ahead to the end without actually doing the work to get the flux that goes through the paraboloid is to say that the total flux, which is the sum of the flux through the paraboloid and the flux through the disk, is equal to the triple integral of the divergence. That's what our divergence theorem tells us. This is going to be a bit of a big brain play we're going to go for here. But so our total flux is equal to the divergence of or the triple integral of the divergence, which means if I separate out the flux and have it as its two pieces, I can move those around on the sides of the equal sign. So I've got my two fluxes, which are the surface integrals added together on the left, is equal to the triple integral of the divergence. That's the thing on the right. So if I want to solve directly, if I want to solve for the flux through the paraboloid indirectly, I could say it's equal to the triple integral of the divergence minus the flux that goes out of the disk. And we'll see later on that the flux that goes out of the disk is just zero, meaning that I can just take the area, the value I already calculated when I did my triple integral, subtract zero from it, and that's the flux out the paraboloid. So that's like big brain play we're going for here. That says that I don't even need to worry about calculating the flux integral out of that paraboloid, because I can use the divergence theorem to know what that value is, which is, a bit crafty, but, certainly something that is nicer than trying to do the paraboloid integral we'll see in a second. But so, I already knew the flux out the disk was going to be zero, so cool. It ends up being zero. But instead, let's just give you a quick overview of calculating the flux directly. If I want to do that, I'm going to need normal vectors, which means I'm going to need to take I need a parameterization. It's actually what I need. So yeah, the parameterization of my paraboloid is going to be that top line that's highlighted in the magenta area. Basically, I already have my parameterization set up because I've got z equals 25 minus x squared minus y squared. So I'm going to pick x is x, y is y, z is a function of x and y, so 25 minus x squared minus y squared. Take some partial derivatives with respect to x and y of those, of that parameterization, get a cross product of that. I end up with 2x, 2y, 1. I know I want my flux to be oriented outward. The paraboloid is the top surface of this solid. So an outward oriented normal vector is going to have a positive z value. So I see that the cross product I have already has positive z because I've got 1 there. All right, cool, that's good. I have the correct orientation for that normal vector. So then, I calculate dp, which is just the integration token that I need for the paraboloid integral. So now you just do, z is a function of x and y. Maybe I call it g. A quick way to get that is negative g partial x, negative g partial y 1. Calculate that out to get dA, and hey, look, I get the same vector that showed up when I did the cross product up above. Is all I really wanted to highlight there. So I need the integral of, well, I'm going to end up needing f dot dp, which is this thing that's starred right there. 4x cubed plus 4xy squared plus 75 minus 3x squared minus 3y squared. So really, that's the thing I'm looking at there is my field dotted with that outward pointing normal vector. You see over here on the diagram, I've got those blue outward vectors point up. But then when I have to calculate the outward flux through the disk, the one at the bottom, that's the bottom face. So now my outward pointing normal vectors are down instead of up. So I want -1 in the z coordinate instead of +1. So positive g partial x, positive g partial y, -1. But that disk is in the plane z equals 0. So my function is z equals 0. My normal vector is just 0, 0, -1. Nice and easy. So then when I do f dot dd, I need my field dotted with that normal vector. I just get 0 because 0 plus 0 plus 0. Well, so that means that when I had to do that extra integral for that, do that, I don't even need to do the disk integral because I can see that integrating it's going to be 0. And then that also lets me skip over integrating this blue starred value that's up here. So I didn't even need to integrate that thing because I used the divergence theorem to find the value instead. And I could integrate it. I don't want to though. It looks hard. Yeah, I don't want to integrate that at all. So I don't. It seemed rough. Divergence theorem helped us out instead. Oh, apparently I left one more for us to talk about. I really thought I was going to be done there. But okay, one last problem to do together. Returning to Stokes' theorem. Uh, what do we have? Another one where it tells us to evaluate the line integral side of Stokes' theorem. So we know that instead, we're going to evaluate the double integral side of Stokes' theorem. So let's just write down what Stokes' theorem is again. Line integral along the curve is equal to the double integral of the curl of f across the region D, ds. Oh, this is actually, it's a surface integral, so it should be surface S rather than region D. If we're still being pedantic about it, which it sounds like I am. So we're going to need the curl, and we're going to need a normal vector. So let's get it. Where do I want to start? Let's start with the curl this time. I have a purple segment. I've got a yellow segment. I've got a magenta segment. All right, and let's start this thing off. I need magenta partial y. So 3e to the xy. Or no, it's not. I'm doing partial y here. So it should be 3x e to the xy. There we go. Minus yellow partial z. So we're subtracting x. Next up, I'm gonna need purple partial z. Yeah. So that's 4y minus that next bit is gonna be magenta partial x. So this will be minus 3y e to the xy. There's a comma there. I'm running out of space. I'm gonna scrunch that stuff up. Our final bit, yellow partial x, is negative z minus purple partial y is 4z. Cool, that's our curl. We'll come back to it if we need it. And we'll come back to it when we need it, because we are going to need it. Oh, we skipped a step. We have a circle. It's x squared plus y squared equals 4, z equals 3. Oriented counterclockwise when viewed from above. The circle is oriented counterclockwise viewed from above. We know this thing has its upward orientation. Up. Okay. So I need a normal vector to go along with this. So I'll take a look at that surface. But this one's got a bit of a shortcut to it. Because we're in the plane z equals 3. Like that is the equation of that surface. I mean, like it's anyway, our region's a circle, but it's in the plane z equals 3. If we need a normal vector to the plane z equals 3, that's just 0, 0, 1. Because it's got to point straight up. But another equally valid way of getting there, we could have done our z partial x and z partial y. But again, z is equal to 3. Both of those partial derivatives are 0. So it's just 0, 0, 1. And again, we want this thing to be oriented upward. So we'll be taking positive 1 instead of negative 1 for the z component. So to figure out what our integrand should be, we need the curl of f dotted with that normal vector we just calculated. Curl f dotted with n. Which is 0 plus 0 plus 1 times negative 5z. Since the z component of the curl is the only one that mattered, simplify that. Negative z minus 4z is negative 5z. Multiply by 1 to get that. And then our curl dot n is just negative 5z. But we need to parameterize this thing so that we're just integrating over x and y. So again, plug in what z is equal to, and z is equal to 3, because that's the plane that we're in. So our integrand is negative 15. Pretty sure that's 5 times 3. Cool. And then it asks us to, pick our x and y bounds here. But, once again, the region we're integrating over is a circle. And we're really just integrating our dA token, negative 15 times our dA token. So we might as well make use of that. The negative 15 times the area of our region, times the area of that circle. Looks like our radius is 2. Back up to the blue region, x squared plus y squared is equal to 4. So this should be pi times 2 squared. We've got a radius of 2. And we can simplify that if we want to. 15 times 4 is 60. So negative 60 pi. And now I think that's the part where I just want to start talking about some concepts. Yeah. So a few more problems that are already done up. So this will hopefully take a little bit of less. These will hopefully go a little faster. That's all I'm trying to say. So verify that Stokes' theorem works for the field provided and the surface S, which is the hemisphere. Again, it's going to be the unit sphere, but this time I'm going to take the right half because I've got y is greater than or equal to 0. So I'm going to set up a parameterization of the surface. Since it's a sphere, I'm going to use spherical coordinates as my guide for creating this particular parameterization. So T and S are my the two variables that WebWork tells me I've got to use. But I want to be thinking about theta and phi. T for theta, S for phi means X will be 1 because our radius is 1. So 1 cosine T times sine S. So cosine theta sine phi. That means that Y is just going to change over to sine theta, still times sine S. And then z is cosine s, or cosine phi. I suppose we also calculated the curl of that thing at some point, but I got -1, -1, -1, or -1, 1, 1. What's next? So this thing was a hemisphere. I think this is the main point that I wanted to talk about in this problem. So we've got a hemisphere. Particularly, though, it is the right half of the hemisphere because y is greater than or equal to 0. So if I want to be putting restrictions on y, I'm going to be focusing on theta and not on phi. Phi is the angle that'll let me put restrictions on z, but theta is what I'm going to go to if I have to put restrictions on x or y. So our normal default is 0 to 2 pi for theta, 0 to pi for phi. I want all of z, so I'm going to keep phi, which is the blue one, s. That's going to stay 0 to pi. But for theta, I'm going to pick out only the quadrants where y is positive. Because I want the positive y quadrants, which means quadrants 1 and 2, because y is sine of theta. So theta is only going to go between 0 and 1 pi instead of 0 and 2 pi. Again, that's because I wanted just the positive values for y. If I had changed this thing up, said I wanted the left half of the hemisphere instead of the right half, so the negative y values, I would pick out the third and fourth quadrants, which means I'd set theta to go between pi and 2 pi. I can even also do the same thing for x. The negative x quadrants would be 2 and 3, so pi over 2 to 3 pi over 2. And if I needed the positive x coordinates being 1 and 4, well, if you're just looking at the unit circle, it's 0 to pi over 2 and then 3 pi over 2 to 2 pi. But a much easier setup for that would be to go backwards to get the fourth quadrant and do negative pi over 2 to positive pi over 2. But anytime we need to be restricting our parameters based on the unit circle, it'll be helpful to think about quadrants. So that really means anytime we go to cylindrical or spherical coordinates, think about the unit circle. We've got to make restrictions. Cool. I did some stuff where we calculated the curl. It's over here on the right. I think that part's okay. Oh no, I've lost some elements over here. Oh wait, no, I'm looking at the wrong problem. Cool. So for the rest of it, I calculated a double integral. I ended up getting this negative pi. The second half asks us to parameterize the boundary curve. And here's another one where we want to be careful for parameterizing this boundary curve. I wanted only the right half, and I want to make sure that I have the correct orientation to get through this thing. So my boundary curve over here, I'm just trying to parameterize the right half of this hemisphere, which means I'm looking at a circle that is in the xz plane, and I'm told I'm going to use cosine theta for x, which makes sense. I'm keeping x around. I'm in the y equals 0 plane, so y is 0. But then the z coordinate ends up needing to be negative sine of t. The reason for that is that if we're going to be thinking about our circle as it's in 3 space, the positive z-axis points up, the positive x-axis points out of the page, the y-axis, positive y-axis points to the right, and I need to orient this thing to have a counterclockwise orientation, be positive. So if you can picture it in your head, I want to take my coordinate plane and rotate it 90 degrees so that the y-axis swings over from the right to come out and in front of me pointing at me. So I can be looking at the xz plane. meaning that the positive x-axis points to the left and the negative z-axis points up. So if I'm going to have my parameterization go counterclockwise with x being cosine of theta, my starting value is going to be over on the left axis. It's going to be off to my left after I've rotated it so that I can be looking in the correct direction. Meaning if I'm starting on the left end, counterclockwise means I go down first and around the circle, which is why I want z to be negative sine of theta instead of positive sine of theta. I think that's another reason why I put this one in here, is just to think about the way that our parameterization's got to get set up. Either way, though, I can then look at my derivative vector, take the dot product of f and dr. I end up getting negative cosine squared, integrate to get negative pi. Ta-da! Cool. And finally, this last problem on here really just kind of brings the whole semester home. If you really want to, scare one of your friends and be like, hey, look at the math that I can do, show them this problem, because this one looks just absolutely insane by the time we try to put it all together. So this is one of our divergence theorem problems. I don't even know what I even want to talk about in all of this. It's a whole mess. But there's a certain je ne sais quoi to it, I suppose. All of this together is really what we've been building toward our whole semester, being able to evaluate both a surface integral and a triple integral, and the interesting ways in which they end up being equal to each other. So I think here must be we were integrating some cylinder that's oriented so that it expands along the x-axis. We can look at a triple integral of the divergence over the solid region. Makes the most sense to integrate it in cylindrical coordinates and see where we're getting our bounds from. The real fun part then is when we try to calculate the flux directly, where I've drawn what our cylinder looks like, but then broken it up into its three surfaces. There's the outer edge of the cylinder down at the bottom, as well as the two circular caps, one that's on the front end, one that's on the back end, and we'll calculate the flux that goes out of each of those, which means a whole bunch of different normal vectors, and just, yeah, look at where all that stuff goes. That's just so much fun. But hey, it's at this point, you've learned enough to be able to do this whole problem, as insane as it looks. So I think this one, I just wanted here so we could reflect a moment on what it is we've actually done this semester, and kind of see how far you've come. So I particularly like this example, not in a way that I'm going to put it on a final exam. This one's going to take way too much time to be able to get done in a reasonable amount of time, along with every other problem that you're going to have to do in a final. So don't expect something that's this complex. This is, again, what we've been building towards, but not something that works out great on an exam. So you'll probably see something not as complicated as this. Expect to see problems similar to other things we did in this exam review. And with that, I do believe that's everything I wanted to talk about on this review. So with that said, if you have not yet taken the post-course survey, remember that that's worth half a percentage point towards your overall grade. They're basically free points. So like, go take that right now if you haven't done it yet. If you ignored the advice I gave at the beginning of pausing the video to go do it, now would be a good time. Other than that, good luck on the final exam, and enjoy the rest of your summer, such as it were. And that's me signing off.